Fourth lecture on magnetic vector potential. Today we shall show some tricky calculation of vector potential. As in first example, we consider a surface current density, a problem of surface current density that we have already evaluated using Biot-Savart law. We consider a surface infinite sheet which carries a uniform current density Js, which carries a uniform current density Js in the direction of J times I cap. Our objective is to find out the vector potential at a point on the axis. So this is the y axis, this is x axis, this is z axis. We consider a area elementary area having coordinate r prime, source coordinate, and our aim is to find out the magnetic vector potential at the field point r, which as per choice of coordinate system lies on the z axis. So the vector potential over here dA at P due to this current density distribution is mu 0 upon 4 pi mu 0 upon 4 pi Js ds prime by r. Now Js is J times I cap, so this is I cap mu 0 J upon 4 pi, and for ds we write it is dx prime do I prime, and for r it is x prime square y prime square z square to the power half. If you want to find out the total vector potential at P, at point P due to this current sheet, then one need to integrate this over the over x prime and y prime. That is to say that A at P is equal to I cap mu 0 j upon 4 pi integration from minus infinity to plus infinity dx prime dy prime to the power half. If we want to find out the y integration is from minus infinity to plus infinity dy prime by y prime square plus s square to the power half, where s square is equal to x prime square plus z square. So the natural way is, first thing is that this is an even integral, so this is 2 times 0 to infinity dy prime y prime square plus s square to the power half. Now we use the substitution to evaluate this. We use the substitution y prime is equal to a tan theta. If we use this substitution, then this is a sec theta, and on the upper half we will have a sec square theta. So the result is 2 times sec theta d theta integrated from 0 to pi by 2. The result is twice log sec theta plus tan theta within limits 0 to pi by 2. This diverges. At the upper limit, this diverges. So we conclude that the total vector potential due to this infinite current sheet does not exist at point P. So the tricky calculation, here comes the tricky calculation. So this calculation does not does not is found to be not fruitful. So what we do? We calculate the magnetic induction or magnetic field, which we generally call it, usually call it, from this expression. So dP, which is the magnetic field corresponding to this, is curl of dAp. So this is mu 0 I upon 4 pi dx prime dy prime, then I cap, j cap, k cap, del x, del y, del z, and then it is along x direction, so it is 1 by r 0 0. So this is mu 0 I upon 4 pi dx prime dy prime. Then this part, no x component because this is 0, j component, del z of 1 by r, and there will be some k component or z component, but this 1 by r doesn't have any y dependence, so it is the field. So now come to the calculation of this. Now del z of 1 by r is equal to del r of 1 by r into del r del z. This is minus 1 by r square, and this part is z by r, so the all together is minus z by r cube. This is not I, this is j. Now this leads to the usual expression for the fields, because this integration can be calculated and we get the result. As for example, if we perform this integration r cube from minus infinity to plus infinity, this is twice dy prime y prime square plus a square to the power 3 by 2 from 0 to pi by 2, 0 to infinity, and this is equal to twice, this is a cube sec cube theta, and on the upper hand a sec square theta d theta from 0 to pi by 2, which is twice integration cos theta d theta from 0 to pi by 2, and this is equal to, this will be sin theta, and this is 2, sorry, I have missed 2 by a square, so this is 2 by a square is the result. This is 2 by x prime square plus z square, and this result, whenever we perform the integration over x, the result is pi by 2, and there will be 4 factor, 1 from 2 factor coming from y integration and 2 from z y x integration, so the b at p on integration becomes minus j cap mu 0 j upon 2 mu 0 j upon 2. There will be some z factor coming, no z, this is for z greater than 0, and this is plus j cap mu 0 j upon 2 for z less than 0. So this is one tricky calculation where we found that the magnetic vector potential due to the entire sheet does not exist at an axial point, but we can still find out the B field. Similar example we have seen in the case of state infinite, where we found that the vector potential corresponding to an infinite state where is infinite or diverges. However, the magnetic field is a convergent one. This is another similar type of example. Another type of example is that the calculation of vector potential from the knowledge of magnetic field. We take this as an example. You know that in this case current is flowing current is flowing in the negative along the x direction. This is the current. Our aim is to find out the vector potential provided that we know the V field is this. So for an infinite sheet, infinite plane sheet, we know that BP, we consider the case for z greater than 0. So BP is equal to minus j cap mu 0 j upon 2, and this is equal to curl of A, and we write for curl of A I cap j cap k cap del L x del L y del L z. And now come to the A component. Since current is flowing in x direction, it will have only x component, no y z component. So this is the field. So if we only j component will survive. So this is the j component. J component is minus del A del Z. So if we compare it with this, we find that A is equal to del A del Z is equal to minus mu 0 j by 2. This leads to that A is equal to minus mu 0 j to z plus some constant. So to say that vector potential is plus some constant which will be in the I direction. This is one tricky calculation of vector potential. Another example, as an example, we consider an infinite solenoid. We know that for infinite solenoid is one for which length is much greater than the radius, and for an infinite solenoid, we know the magnetic field. The solenoid is assumed to be one which is along the whose axis is along the z axis. This is A, radius is A, and the current is flowing. Current I is flowing, so this is known as k cap mu 0 n I for rho less than or equal to A and 0 for rho greater than A. That is, if we consider the field, then within the solenoid the field is uniform, is along z axis, and outside the solenoid the field is 0. our aim is to find out A. Since the current density, the surface current density is Ni along phi cap, the current is phi, we know that the corresponding vector potential will be something times phi cap. So for internal point, rho is less than A, that is within the solenoid, we write this A dot dr over a closed path is equal to curl A dot ds is equal to B dot ds. If we want to find the magnetic vector potential at a distance rho from the center, we assume a circular path of radius rho such that the center of the circle lies on the axis and the plane is perpendicular to z axis. So it is in xy plane. The circle is in xy plane. So at every point on the circle, dr is along the phi cap direction and A is also on the phi cap direction. So on such a path, which is very similar to the Amperian path used in connection with the derivation of magnetic field using Ampere circuital law, we find that A and dr are parallel, so that this integration becomes A has the same value everywhere on the periphery. So this is equal to 2 pi rho A1. A1 means the point is within the solenoid, and on the right hand side it is the surface integration that yields you B is uniform. So B, this is pi rho square times B B1, and B1 is this the magnitude pi rho square mu 0 Ni, where n is the number of turns per unit length. On simplification, A1 comes out to be, says out, rho. For external point, that is, if we consider a point lying outside the solenoid, for external point, rho is greater than A, and we, using this similar thing, we get on the left hand side 2 pi rho A2. A2 is the vector potential outside, and in this case we see that the flux is linked only up to a circle of radius A, and for the circle of annular ring of radius starting from A to rho, no flux is linked. So this will be, the situation is that this is a circle of radius A, and we are considering for second path, it is the path 2 of radius rho. This part is linked with the flux because the magnetic field is non-zero within the solenoid, and for this part B is equal to 0. So this right hand side can be, the surface integration can be converted into this integration over S is a circle of radius A plus annular disk. This does not contribute anything because the field is 0. So this is mu, and this is pi S square mu 0 n I. On simplification we get A2 is equal to pi cancels out, S square by rho. So we find corresponding to this situation, compared A is along phi cap direction, A is along the phi cap direction, mu 0 n I by 2. For internal point it is rho, for rho less than equal to A, and this is A square by rho for rho greater than A. So the variation of field vector potential is like this. This is for a solenoid, the variation of. Another type of example is that sometimes the current density is supplied and one need to find out the vector potential. As the last example on the calculation of vector potential, we consider a cylinder of radius A, a cylinder of infinite cylinder of radius A, which carries a uniform current density. Uniform current density, volume current density is that J is equal to K cap J0 with constant. Our aim is to find out the vector potential. Obviously, we know that the vector potential in Coulomb gauge condition satisfies this equation. So to say, del we can solve this equation in this way or using cylindrical coordinates, but here we shall not go to the solution of this differential equation, because the semester 2 students are not yet accustomed with the solution of partial differential equation. So we perform a tricky calculation that again we convert it into the problem that B is known, and from the knowledge of B we shall find out A. So if we apply Ampere's circuital law to the internal point region 1, then the internal region the field is 2 pi rho B1 is equal to pi rho square J0. So this gives you pi cancels out. Mu 0 term is missing. Mu 0 term, we have applied Ampere's circuital law, so this is mu 0 by 2, mu 0 by mu 0 J0 by 2, and this is rho. And for external point, this is the external point. If we consider external point, then this is 2 pi rho B2 is equal to mu 0 pi S square J0, or B2 is equal to mu 0 J0 by 2 S square by rho. Just similar behavior in the case of solenoid, we found that this is the behavior of A. Here it is the behavior of B. Now since the current is flowing along the z direction, A will have the z components only, and we write that B in vector form. B is equal to phi cap mu 0 J0 by 2, and it is rho for rho less than equal to A, and it is A square by rho for rho greater than A. So we write it as curl of A, and we write the expression for curl in cylindrical coordinates, which is as current is flowing in the k direction, the vector potential will have only the k component. And if we compare this expression with the phi, it will have only phi component. So this phi component is this, when multiplied rho gets cancelled. So this is minus this, minus del rho of A. So in comparison with this B field, we find that del A1 del Z, that is for internal point, the potential is phi cap cancels out. So this is equal to minus mu 0 J0 by 2 times rho. I have written something. This should be rho. This gives you A1 is equal to minus mu 0 J0 by 4 rho square plus some constant C1. And for second point, external point, a square by rho, and if we integrate it, we get A2 is equal to C2. So this is the expression for the vector potential at an internal point, and this is the vector potential at an external point. And note that vector potential is only have k components. So in vector form, it will be multiplied by k cap. So these are the few. So let me finally write the potential as A mu 0 J0 by mu 0 J0 is common, minus k cap mu 0 J0 is common. And for internal point, we will have minus 1 upon 4 rho square plus C1 . So by the 4 lectures, a series of 4 lectures on vector potential, we have completed the theory of vector potential and have worked out lots of calculation of all possibilities for the calculation of vector potential.